Hello dear listeners and viewers. In this video I will introduce a few more important concepts and misbeliefs of quantum science. In everyday life we often observe interference of water waves. This is the phenomenon of amplification and weakening of interacting waves with the appearance of standing or traveling patterns ordered in space. You can easily see interference just in a plate with water in bright side lighting. Interacting with barriers, primary waves generate secondary waves, interference of secondary waves behind obstacles, and in other areas inaccessible to primary waves is called diffraction. Light can also exhibit wave properties and create regular diffraction spots, circles, and lines on the screen behind specific obstacles containing sharp edges, small slits, or irregular grooves. For example, I can direct a beam of light from a laser pointer or a laser rangefinder just perpendicularly to an unneeded CD disk and see a set of spots on the wall. The central spot is explained by the regular reflection as in a mirror, while the accompanying spots arise from the phenomenon of diffraction on CD grooves. So, diffraction is a crucial property of all periodical space waves. Thus, observation of diffraction of atomic particles such as electrons would prove correctness of both concepts of de Broglie waves and Schrödinger wave functions that underlie quantum theory. The first such experiments were made in 1927 by Clinton Davison and Lester Germer, and independently by George Thomson. As in our demonstration with the laser beam, Davison and Germer aimed a beam of electrons just perpendicular to the surface of a nickel metal crystal and measured the reflected electrons at different angles. They observed a peak in the reflected electron flow initially accelerated to a potential of 54 volts at an angle of approximately 51 degrees. This result can be explained by the interference of de Broglie waves. We know that two identical waves reinforce each other if travel together. The same happens if two waves from synchronous sources travel equal paths to the point of overlap, because crests of one wave meet crests of the other wave and troughs meet troughs. If there is a path length difference of half the wavelength, then crests meet troughs, and oscillations of two waves kill each other, for both cases of coupled and colliding waves. If we further increase path length difference, then we see maximum amplifications of oscillations every time if path length difference is equal to integer number of wavelengths and see minimums in between. The Davison-Germer experiment is explained by superposition of de Broglie waves that are reflected from adjacent rows of atoms in the nickel crystal. The distance d between rows is 0.22 nanometers. Path length difference b between two neighbor waves reflected at an angle alpha is equal to d sine of alpha. Amplification happens if it is equal to one wavelength lambda. For acceleration with a potential of 54 volts, the wavelength lambda is 0.17 nanometers. From this condition we determine the angle. It is equal to 50.7 degrees. This is precisely the value observed in the experiment. In order to simulate George Thomson's experiment on electron diffraction using an analog with a laser beam, we will take a glass lid from a kitchen pan and place it under a stream of steam from a kettle. Then we will direct the beam from the laser pointer through the glass to the droplets of condensation. Here we will see diffraction rings on the screen behind the lid. Instead of layer of condensed vapor droplets, George Thomson used gold foil with metallic gold microcrystals. Instead of our laser pointer, Thomson used an electron gun. Electron diffraction rings were observed on a photographic plate. The origin of rings is as follows. Diffraction of electrons on an individual microcrystal is similar to the diffraction of a laser beam on a CD disk. We have seen that all reflected rays, including the principal mirror ray, lie in the same plane, which is perpendicular to the direction of parallel grooves on the CD, or atomic rows in the microcrystal. Then if you move the incident ray to another place with another orientation of grooves, then the principal mirror beam remains almost in place, but the diffracted beams rotate around. The same rotation we see for refracted rays if shine through the CD or use glancing incidence and rotate the reflecting surface. In general case, the path difference in diffraction by a microcrystal occurs due to reflection from different crystal planes, as shown in the figure. Amplification of reflected waves happen if 2d multiplied by the sine of glancing angle of diffraction theta is equal to integer number of the Broglie wavelengths. This formula is called Bragg's law. Thus, the rings in Thomson's experiment are formed due to diffraction at different and randomly oriented microcrystals. It is thought that experts in crystallography can attribute the rings and their sizes in Thomson's experiment and associate them with different crystallographic planes in gold microcrystals using the Bragg's law. In reality, it is not easy to do. That's why let's just take it on faith that the experiment can be explained in this way. At the same time, it is important to know that in many textbooks the Bragg's law is used to explain the Davison-Germer experiment. Some authors also refer to so-called reciprocal lattice and the L sphere. I am sorry, but most likely these explanations are wrong for Davison-Germer case because diffraction planes in this case need to be constructed with very deep and widely spaced atoms, and then diffraction effect is just weak for these planes compared to simple surface diffraction assumed in our review. Nevertheless, in any case, the Davison-Germer and Thomson experiments confirm the validity of using the Broglie waves for electrons. However, there is another group of diffraction experiments that can be interpreted completely differently. I'm talking about electron diffraction by single crystals. Then instead of rings, we see odd spots on the screen. The analog with light diffraction is as follows. We direct the laser pointer beam to the plane of the bird's feather. A certain structured system of light spots is visible on the screen placed behind. A very similar picture is observed in laboratory equipment used in universities in educational courses. For example, this is the picture observed during electron diffraction on a properly rotated single crystal of graphite. In my view, it looks as just an obvious result of a particle flying through a series of obstacles with side impacts. To explain how it works, we will now use so-called Monte Carlo method for simulation of physical processes. Let an electron fly through 3 layers of planes with hexagonal graphite cells, and there is a probability of being hit in each layer. It is like a quest with swinging obstacles. We will use these red dice to simulate the probability of a hit in each layer. If a 5 or 6 is rolled, then the strike has occurred. The probability of getting 2 dedicated sides out of 6 is 2 divided by 6, or 1/3. Thus, the probability of getting a side impact is 1/3. Further, we assume that in the hexagonal cell, 6 equally probable directions of impact are possible. We will play these directions using this green die. Rolling a 1 means hitting up, 2 hitting to the next point clockwise, and so on. Now the first Monte Carlo draw. Drop the electron to the screen center. First layer pass, no hit. Second layer, no hit. Third layer, no hit. Draw the electron in the screen center. Second Monte Carlo draw. First layer impact. Play direction 2 to this point. Second layer pass. Hit again. Direction 3. Move it here. Third layer, no impact. Draw the electron on the screen. Then continue. After 300 rounds, we have the following picture. Compare with the experiment, just a great quality match. Pay attention to this spot and this another spot. The shortest paths to both spots consist of 2 hits, but if there is only one way to the first spot, then there are 2 ways to the second spot. As a result, the second spot gets twice as many electrons and it is much brighter than the first one. Fine, we explained the experiment at a qualitative level, but how about a quantitative description? To estimate value of the side impacts, we will use so-called uncertainty principle, introduced in atomic physics by Werner Heisenberg in 1927. It says that in all observations and interactions of an atomic particle, the product of uncertainties in its coordinate delta x and momentum component px is greater than reduced Planck's constant h bar. This uncertainty relation can be used in the form of the exact equality if we can determine the proper size d based on the conditions of the interaction process and substitute it instead of delta x. both in the general case of a symmetrical environment and in the particular case of the hexagonal graphite cell. Parameter d can be determined from simple additional rules listed here. You can see some possible candidates and the winning one. Flying inside the crystal, the electron can receive elastic side impacts. Directions of its velocity and momentum undergo a change, as shown in the figure, but its energy and absolute velocity remain unchanged, and we can redraw the figure without vectors. Sine of the refraction angle beta is equal to ratio delta px over mv. Substituting delta px from Heisenberg's uncertainty relation, we obtain new equation. But we have already met the expression from the right side many times. This is exactly the de Broglie wavelength lambda. So we have d sine of beta is equal to lambda. We have already obtained similar expressions a little earlier based on the concept of de Broglie waves. Now we have the same result based on the concept of particle momentum and uncertainty principle. This does not mean any contradiction. Both concepts of de Broglie waves and the uncertainty relations are just useful simplifications. According to today's knowledge, a more complete picture is given by solutions of the Schrödinger equation. We can also determine from the figure that sine of beta is equal to x divided by the hypotenuse. But the sine is equal to lambda over b. By squaring both parts of this equation and further transforming, we can get the final formula. The speed of the electron is related to the accelerating potential of the electron gun u by the energy conservation law. From here, we can express lambda through u and draw a graph of x versus u. We see excellent agreement with experimental data. Note that for small refraction angles beta, the distances x between all spots on the screen are approximately equal. Well, we have just described electron diffraction using a corpuscular approach, but can we do the same coming back to Davison-Germer experiment? The answer is yes, we can. If we repeat calculations similar to those just made, we obtain the angle of preferential electron scattering of 51 degrees, which is in a good agreement with experiment. Now what we have is a dry extract. In some simple cases, electron diffraction patterns can be forecasted by de Broglie waves or uncertainty rules. In more complex cases, we must use more complex tools, like the Schrödinger equation and various types of its approximate solutions, also called path integrals. Both de Broglie waves and Schrödinger wave functions give us powerful and reliable methods for describing processes in the atomic world. But these waves are waves of probability and exist only in theoretical calculations. They do not exist in nature as physical objects and do not carry any mass. Mass transfer is carried out by electrons as particles. Electrons as carriers of mass and probability waves are different objects. The size of the electron is much smaller than the size of the area occupied by the fields of probability waves, such as electron clouds, de Broglie waves, wave functions, etc. We can compare de Broglie waves with legend symbols on a very simplified map of the area and compare the electron with the traveler who walks through this area. The land map itself is similar to a chart of the wave function. Then, knowing that the traveler left point A, we can assume that he will come to point B or C, but at the same time we do not know how the traveler goes, along one path, along another, or along some other path. We also do not know for sure what this area really looks like a sunny beach with palm trees or like a snowy forest. Quite similarly to that, we do not know what the atomic world actually looks like and what processes stand behind validity of probability waves. The traveler can choose different paths based on current random events, such as meeting a crocodile or meeting a bear. In a similar way, the movement of an electron as a particle occurs along trajectories that can change directions randomly due to interactions with other objects. In some cases, describing the motion of an electron as a particle using predetermined or random trajectories simulated by Monte Carlo methods can be more correct, simpler, and more understandable than the wave description. We have just shown this using the example of diffraction on a single graphite crystal. In conclusion, we note that here we did not touch at all on the extremely interesting topic of the so-called double-slit electron diffraction and related issues. I am going to cover this topic in a separate story.